Hoffbauer back. Hope we're doing okay. We are going to talk about lesson 1.3 today. Continuity, which is mostly a discussion you'll have in calculus about the different kinds of continuity. We're going to look at them today, but not super important. This discussion about end behavior is really important for us this year. And limits is a way to talk about end behavior that you will use at the end of this course. We'll get into it, and then it's the stepping stone for where you start in calculus. So for today, we're going to talk first about continuity. A graph is said to be continuous. Any chance I can spell that right on the first try? Continuous. If there are no gaps or holes. Gaps is also said to be breaks, okay, of any kind. So you can trace it out with your pencil without ever picking your pencil up. So there are no breaks or holes in the graph. If there are, breaks or holes in the graph, then it is said to be discontinuous. I don't know if I spelled that right either. Okay. So there are three types of discontinuities that you will see eventually. If the graph has a vertical asymptote somewhere, then it has an infinite discontinuity. In other words, it's discontinuous all the way up and down this line here. It is a complete break from left to right. It has a jump discontinuity, mostly in piecewise functions. If the value stops down here and then it jumps up here and has an open circle, or the other way around, okay? It can also have just simply a hole in the graph. We will see a few of these in rational function chapter. Excuse me. And that is called a removable discontinuity, or just a hole. So in your notes, we're going to write these down real quick. We have an infinite discontinuity when we have a vertical asymptote. Oh, what happened? My cursor quit working there. Okay. This is a jump discontinuity, when it went from one place to another, and these usually happen in piecewise functions. They don't always happen in piecewise functions, but that's where we see that the most often that happens. And this is called, was it a point discontinuity? Or down here it says it's also called a removable discontinuity. Okay, and we just can call it a hole for this year. And it has a hole where x equals a. So functions that are not continuous are discontinuous, and they can have any of these three kinds. We will talk about them, but they will not be on an assessment where you have to tell me the kind. You might be asked if it has continuity, but I'm not going to ask you the kind on an assessment. All right. Determine if the function shown is continuous. If not, identify the type and location. Location is by x value. So this is not continuous. I can't trace it out with my pencil without jumping here. And that is what the kind is. It is a jump discontinuity. And it occurs at, let's see, if this is the origin, x equals -1, 2, 3, 4, 5. All right, this one I can trace completely left to right without lifting my pencil. So this is continuous. This one, if I trace from left to right, I get a place in here where it is infinitely discontinuous, or it has a vertical asymptote. We'll talk a lot more about those later. So this is called an infinite discontinuity. And it occurs, it looks like at x equals 1. Again, on a test or quiz, I will only ask you if it is continuous. Oops. Just a couple quick more here. This one goes left to right smoothly, so this is continuous. This one has a hole at 1, 2, -3, or a point discontinuity or a removable discontinuity. And this one actually has 2 discontinuities. It has a line or infinite discontinuity at x equals, what is that, 2? And then over at x equals 4, it has a hole. Okay, not going to ask too much about those, but easy peasy to do on the homework. All right, here, these are the kinds that our pre-calc book asks more about. It says, are these continuous? And that's all, just yes or no, okay? If you were to think about this graph, it's just a parabola. I don't even know where it goes or if it crosses the x-axis, but it is continuous because it's just the graph of a parabola. If we put a value of 4 in, we get 16 plus 20 plus 3. What you would do in calculus is you would check on both sides of 4 really closely to see and make sure it was continuous on both sides, like put in 3.99 and 4.01 and make sure it still works and that the values are all close together. And what does that come out to be? 39? And they would all be close to 39. This is just, yes, it's continuous, and really we could have just figured that out by the graph. This one, I have an error on my slide that I didn't catch until now. I believe on your paper it just says x equals 1, or it should. And it asks, is it continuous at x equals 1? If we were to graph this on the calculator, you would need parentheses around the bottom for sure. I would teach you to put them top and bottom. And it's going to have some asymptotes, okay? Because if I factor the bottom, factors x minus 1 and x plus 1, this and this are undefined places. So the question is, what happens at x equals 1? Well, if I put a 1 in top and bottom, I get 2, but down here I get 1 minus 1 is 0. You can't divide by 0, so it is undefined at 0. I'm sorry, at 1. So it is, no, it's not continuous. It actually would be infinitely discontinuous there, but all they want is yes or no. All right, and then the piecewise. These are the ones that seem to stump students. A piecewise graph, whoa, I don't know what that is. A piecewise graph simply means that it has different pieces. Now it could be a parabola hooked to a line. Oh, not that line probably, but it could be an absolute value graph. Then it jumped over here to a parabola, okay? The question is, when the rule changes, does it meet up with the last rule or not? Okay, when the rule changes at 2 here, are they at the same spot or does it jump? So it asks us, is this continuous at x equals 2? That's the question. So if the rule says I should put the 2 into the bottom because it says less than or equal to 2. If I put a 2 in down here, I get 2 minus 1 equals 1. So when I put a 2 in, I get out a 1. But there is an open circle at this spot where x approaches 2. And if I put a 2 in up here, I get out 5. So when I put a 2 in up here, I get a 5. We're going to learn more about these next week. But when you graph this, this would have an open circle and this would have a closed circle. So the question is, do they meet up? And the answer is no. The graph of this actually looks like, there's a slope of 2, it crosses at 1, which would be here. And then over here, the slope is crosses at -1 and has a slope only of 1. So it is flatter. So it would look something like this, but it would have a jump in it. So because when we put a 2 in this and this, it did not meet up at the same place, it is not continuous. All right, so that's the first half of the video. We got done in 10 minutes on continuity. The second half here, we're going to talk about end behavior. And some students get the hang of this super quickly and others really struggle with this. What I need you to understand is there are 4 things we need to talk about: left, right, up, and down. Okay? The end behavior of a function describes how a function behaves at either end of the graph. That is, end behavior is what happens as the values of y, or f of x, increase or decrease without bound, becoming greater and greater or more and more negative. To describe the end behavior of a graph, we can use the concept of a limit. So the left end behavior would be what happens when x approaches -infinity, okay? I want you to think of the x-axis, and it's going to the left, so it's going towards -infinity. This means left. Whenever you see x approaches -infinity, we do not use this limit notation. You will use this in calc. We're just going to say this, okay? And x approaches -infinity means that it's going to the left. Think about the x-axis. The x values get more and more negative as you go left. The right end of the graph is what happens as x gets bigger and bigger or approaches infinity. Again, x-axis runs left and right. As you go to the right, the values get bigger and bigger and bigger, so they are approaching positive infinity. So x goes left to right. And what you have to describe about the end behavior is what the y value is doing. The y value is going up and down. So this means y, okay? The y-axis runs up, where the values get really big. So when you see a positive infinity, the word for this is y is going up. And when you see f of x approaches -infinity, the y, f of x means y, are getting more and more negative. So it is going down. You need to understand those 4 phrases. So important. Left, right, up, down. All right. So the end behavior of a function describes how the function behaves at either end of the graph, or what happens as f of x increases or decreases without bound. You can and will in calculus use limits to describe this, and it will look more like this. F of x as x approaches -infinity. Well, we write as x approaches -infinity, that simply means on the left, because the x-axis runs left, right, and it's negative on the left. Then we describe what is the y doing. Well, on any graph, it could be going up or down, or even staying constant. We'll talk more about that. But we have to fill that in with some kind of value for what y is doing, okay? The right end behavior, in calculus, you would say the limit as f of x as x approaches infinity. In other words, as the x values get really big, we're going to say as x approaches infinity is the right. What's happening on the right? Is the y going up or down, or staying the same? So the function may approach -infinity, positive infinity, or a specific value. So if you were to see this, this means the y is getting more negative. The y runs up and down. More negative would mean down. If you were to see this, f of x, that's y again, is approaching positive infinity, that means it is going up because it's getting bigger and bigger values. And when you see x, remember x runs left or right, so more negative would mean you're going to the left. And when you see x, again, left or right, but positive means it's going bigger and bigger, so it would be to the right. So you must understand how to translate these into the words, so then we can talk about the actual picture and how we write them. All right. So as x moves towards positive infinity, that means left, and negative infinity, whoa, I just said that backwards. Scratch that, guys. As x moves towards positive infinity, that would be right, and negative infinity would be left. This is x, would be negative infinity over here, positive infinity over here. What is happening to the value of y? Well, if I put my pencil on this graph where it crosses the y-axis, as I go towards the left, this graph goes up. So I need to say left, the end of the graph is going up. To say that, I say x is approaching negative infinity. That means left. The y values are going up. Now, sometimes it will be written like this, where they put the x first and then the f of x. But we do it in Algebra 2 like this, I believe, so we're going to stick with that notation. Okay, just wherever the x is, it means left or right. Wherever the y is, it means up or down, whichever order they decide to write it in. All right, so this one, now you can't repeat this. You have to say the other side. We already did left, so now we need to do right. And the x value goes to the right, means it's getting big. And then what is the graph doing as it goes to the right? So if I find the y-intercept and I go off to the right, it is going down forever. So to say it's going down, I say the y values are getting more and more negative or down. Okay, so you always have to have a left and a right, and then the up or down depends what the graph is doing. But you always need x to have a negative infinity and x to approach positive infinity so that you describe the left and the right. You can't do x infinity both, but you can for y, okay? The y value can both be going up. The y on this end goes up and the y values go up on this end. So this time we say the left is up and the right side of the graph is up. So to say left, we say x is going towards negative infinity, the x-axis off to the left. All right? And when it goes off to the left, the graph of the function goes up, so we say y is getting bigger. To say it goes to the right, we say x values going further to the right are getting bigger and bigger, and as the x values get bigger, the graph of the function is going up. So this time both end behaviors are up for the y values on the left and the right. All right, so this one, the left end is pointing down and the right end is pointing down. So we say the value of the function approaches negative infinity or down as x approaches negative infinity. So that sentence right there means it's down on the left. And then if we want to say the right, we say x approaches infinity, that would be the right, and it's also down, so we say negative infinity for the y as well. Remember, the x has to have both left and right, and then whatever is going on the graph determines the y. These are both going down, so we have negative infinities for both. All right, now this graph is not continuous. Okay, it's discontinuous in here at x equals, I can't tell, -1 maybe? But end behavior, remember, only talks about the far left and the far right, so we don't care. We just want to talk about as it goes left forever and right forever. We don't need to describe what's going on here as long as they only ask for the end behavior. So to say that it is going down on the left, okay, as x goes further to the left, the y values, or f of x, are going down, -infinity. So this means on the left, it's going down. To say that on the right, it's going up, I have to say x-axis goes off to the right. Those numbers are bigger, so I say infinity. And then f of x is going up, and up would be a positive infinity. Okay? You really have to get good with the words so that you can translate the symbols. All right, the final option for this is that a graph can sometimes approach a value. So as x goes off to the left forever and ever and ever, and off to the right forever and ever and ever, it appears that this is getting closer and closer to a y value of -1 down here. Now there is also a break in the graph at x equals -1, but remember, end behavior is what's going off to the far left and the far right. So we want to say left. We say -infinity for x, because the x-axis is going left. It is getting closer and closer to a y value of -1. If we want to say to the right, we say x is getting bigger and bigger as we go to the right, but the y value is staying very, very close to -1. So it is possible for a graph to simply approach what's going to be called a horizontal asymptote or a single value. So real quick, this one appears to get closer to 0 for y. So f of x is approaching 0 on both sides. And if we want to say left first, which there's no requirement, but we usually do left first, we say as x is getting more negative, and then right would be as x is getting more positive. Now this is one where only one of the directions is approaching a singular value. This one is going up, 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 up on the left. So we say it's going up towards infinity as x goes left, which means -infinity, because x is getting more and more negative as we go this way. But on the right, the value doesn't ever seem to move past a y value of 1, 2, 3, 4, 5. It appears that the y on the right stays very close to -5. So the y value stays at -5 as x gets bigger and bigger and bigger off to the right. All right, one more. This one seems like the y values are staying. It's not really a very good graph because it doesn't go out very far, but it appears that they're staying right about at, what is that, 2? Y equals 2. And again, we don't care that there's a break in the middle. For end behavior, we just say off on the left as x gets more and more negative. This graph is staying right about at 2. And on the right, it is also approaching 2. It's from above. This stays just below 2, but we don't care. It's just out on the ends. What is it close to? And to say the right side, we say the x's are getting bigger and bigger. All right, I have a few more examples. If you're thinking you've got it and you want to not watch the rest of the video, it's your call, but I'm going to go ahead and do these on the video rather than just as examples in the notes, just because I think verbally it helps. This graph is down on the left and up on the right. All right, so the left would mean x is getting more negative, and the right would mean the x-axis goes across to the right, would be approaching positive infinity. All right, the y values, to say it's going down, we would say the y's are getting more negative. To say it's going up, we would say the y's are getting more positive. Hope this is making sense, guys. And this one, do real quick, but both ends are going down. Both y's are going down, both the left and the right. So this is getting more negative and more negative, the y's, okay, down. But it's doing that as the x goes to the left and to the right. And then we have a couple more examples of continuity. If we put a -4 in here, we get a 0 in the denominator. If we put the -4 up top, we actually get -6. It is undefined, so determine whether it is continuous. The answer would be nope. This graph, if you graphed it on your calculator, is a smooth continuous curve. Okay. By the way, I should talk about this. This graph, let me think. I think would look like this. Oh, it would be over here. Okay. If you were to graph it. So while it is discontinuous at -4, it is actually continuous. If I had said at x equals 2, when you put a 2 in there, you would get 0. I didn't do it well, but at x equals 2, you put a 2 in here, you would get a 0 over 6, which is 0. So at 2, it has a point of 2, 0. So it actually crosses the x-axis at 2, but it is continuous. Okay? So a graph can be continuous at other places. All right, moving on. Not something I'm going to ask you necessarily, but here, this is what this graph looks like. I have no idea if I'm even close to the right. I know the left end is down and the right end is up because of this, but it is a continuous graph. So when I put a 1 in, I get out 1 minus 2 is -1 plus 2 is 1. It's continuous. You could just look at the graph. Piecewise, remember, can jump anytime that it changes rules. So this graph, I have no idea what it looks like, but if it had a cubic and then it had a solid line and then here it had a parabola, okay? It's not necessarily what it looks like, but my question is, do they meet up? Does this line actually connect these, or is it somewhere else? And I can tell that by putting in the values and seeing whether it jumps or not from one to the other. If I put a -2 in here, it would be an open circle because it's not an or equal to. But if I put a -2 in, I get 2 cubed is 8. So when I put in a -2, I got out an 8. If I put a -2 into the middle rule, it says all I ever get out is a -10. This would have been an open circle. This would be a solid circle. And this value would be an open circle. It does not include this. But if I put a -2 into that equation, let's see, that would be 4 minus 16 is -12, minus 1 is -13, I think. So it does obviously jump around in different places at the end points of the graph. So this is yes, it is just no, sorry, I didn't say that right. Is it continuous? And the answer is no, it's not continuous. All right, that's it for the video. The assignment is also very short. There's just a few questions on a worksheet. It's a practice worksheet 1.3 in the Google Classroom, and make sure you check your answers when you're done. Thanks, guys.